Hello everybody. In this video we are going to talk about intermediate code generation. So we know that most compilers, they convert from source language to some target language. That is the work of the compiler. So it takes as input a source language and produces a target language. Now most of the time this target language is either assembly language or machine language, whereas the source language is usually some high-level language. Now this direct translation between this high-level language to the machine language or assembly language is slightly complex. Okay, and also the machine language or the assembly language that has to be generated, you cannot make certain optimizations if you directly do this translation. So instead what is done is that first this high-level language constructs are converted into an intermediate language. Now this is intermediate in terms of complexity between the source language and the target language. So it becomes easier to convert from high-level language to intermediate language, and then after performing certain optimizations and all, we can convert from intermediate language to assembly or machine language. So this intermediate code, there are different forms of the intermediate code. So let's see what are these. So types of intermediate code. So we have postfix notation, we have syntax trees, and we have tree address codes. So in our discussion in this video, we are going to concentrate on postfix and syntax trees, and tree address codes. We are going to look into details about this. We are going to see this in the next video. So let's see first with a postfix notation. So we are all aware of the postfix notation, how to write a postfix notation. So if I have an expression like this, a plus b, the postfix notation would be ab plus. So we can use this also for our for representing our programming constructs also. So if I have something like this, say if a, then b, else C. This is a programming construct. So you can write this in the postfix notation as A, B, C, and then this is the ternary operator. This is a ternary operator. So if A, it is interpreted as if A, then B, else C. So this can be expanded to any number of conditions. So like I can have nested ifs also. So if A, then I have a nested if. So if C minus D, then A plus C, else A into C, else for the outer if, else A plus B. So for this whole thing, we can write it as A, C, D minus A, C multiply, then comes our ternary operator, okay. A, B plus, then for the outer if. So for programming constructs also we can write like this. So if you have your loops, that also you can write in using postfix notation. Now how do we evaluate? What is the evaluation scheme? So for the evaluation, this is evaluated through the use of labels and jump statements. Now this jump statement may be conditional, like say jump if 0, or unconditional. So jump if there's no if, just jump. Okay, so label we can indicate like this, L1 colon. Okay, so this indicates that L1 is a label. Okay, or a jump, I can have something like this, label. I can have a label and then I can have jump. So this is an unconditional jump to this label. Then I have I can have something like this, value label jump if equal to 0, JEQZ, jump if equal to 0. Okay, so if the value of this is 0, then jump to this label. So the value of 0, value 0 indicates the condition is false, and 1 indicates it is true. Or rather, I should not say 1, any other value indicates, any other value will indicate that it is it is true. So with this, let us see an example again of an if. So if E, then X, else Y. So if I have to write it in a postfix notation, I will, using labels and jump, I will write it like this, E1, L1, jump if equal to 0 to, this is Z, to X, label 2, jump. Okay, and what is label 1? Label 1 starts here, Y, and label 2 is the end. So if you see this here, this is E is the value, L1 is the label, jump if 0. So if E is 0 means if E is false, jump where? Jump to L1. And what is L1? L1 is Y. So if E is false, then jump to Y. Okay, if it is not equal to 0, if E is not equal to 0, then it will go to the next point, which is X. Okay, so this is true. So this will be evaluated. So if E is true, then it will go to X. Okay, then it will go to L2. Now L2 jump here means jump to L2 without any condition. So there is no condition. So jump to L2. So L2 is what? L2 is the end of the structure. So we can represent our tree address code, our intermediate code in this manner. So the code, we can put it in a this whole thing is our intermediate code. So this we can put it in an array. Each one can be each element can be either an operator or an operand. Okay, so if it is an operand, like here E is an operand, X is an operand, so these will be pointing to symbol table. This will be pointing to the symbol table entries. Okay, and if say it is a operator like this, then it will be some instruction code, some opcode will be used. Okay, and these labels will basically be like here. You see, if I have this here, so label here will mean the index of the element which we are trying to refer to in this array. So L1 here would refer to index number, say 1, 2, 3, 4, 5, 6 and 7. So L1 would be 7. So this is the index of the array element of the array which is holding the intermediate code. So this is for the postfix notation. So we can look at the syntax directed translation. the syntax directed translation for this. So I can have, if I have something like this, E is E1 op E2, then the semantic action would be E dot code. By code I mean the intermediate code for E is E1 dot code concatenate E2 dot code concatenate, and then you put the operator at the end. Okay, and E, I can have something like this, another production. So the semantic action here would be E dot code is your ID. So this is assignment. So is ID. Okay, and you can also associate program segments to perform each of these. Like say for example, to do this, what do? You just do print the operator. Code will already be generated by this one. Okay, so by this. So for this second one, we can have simply print the ID. Because if you look at this here, what do we have? We have the operands, which is ID, and we have the operators. Okay, so this is your postfix notation of intermediate code. Then we have the second type of intermediate code we're going to discuss is our syntax trees. So a syntax tree is similar to your parse tree. Okay, and here it is quite a useful representation of intermediate language, and it is especially useful when we want to perform some optimization of the code, because that requires a lot of restructuring. So with a syntax tree, we can perform this optimization in a better way. So the SDT, let us look at the SDT for syntax tree. So if I have something like this, E derives E1 op E2, I can have the semantic action as, say, E dot val is, we have a function here, node, create a node with operator, then left child and right child, E dot val. Okay, so if I have something like this, then I get this. Then if I have, say, unary operator, E is minus E1, okay, then E dot val would be unary, then operator and E1 dot val. And if I have ID, E derives ID, then E dot val would be equal to leaf, make a leaf node, that is, create a leaf node with the label ID. So here operator indicates the root, this indicates the left child, and this indicates the right child. In case of unary, I have, this is the parent and this is one child only, and here this means make a leaf node. So if I have an expression like this, 2 plus 3, so minus 2 plus 3, okay, then I get the first one is minus, okay, so minus is an operator, then I get 2 is a ID, so make leaf ID, then minus 2 becomes, I do unary, I call the unary function, and then I make this the root, and then to the child node. Then I have plus, what is the operand? Operand is whatever is here, and 3 here. So this is the syntax tree for representing this particular expression. So again, you can also try this out for your constructs, programming language constructs like if and loops. So both postfix expression and syntax trees are good representations of intermediate code, but something which is more close to the actual implementation is our tree address code. So we will discuss tree address code in our next video.